Continue on Physical Chemistry, Chapter 19, Section 3. Now we're in the second half of Section 3. So we're going to talk about ionization energy and ionization potential. So let's say we have the absolute value of energy in the ground state. So this is the energy in the ground state. So absolute energy of the ground state, that's also the ionization energy. So in case of hydrogen, that'd be 13.6 electron volts. So we say the ionization potential is minus 13.6 or negative 13.6 electron volts for hydrogen. Now let's talk about atomic units. So energy is going to be expressed in Hartrees. So one Hartree is equal to E prime squared over A sub 0. So we get 27.211 electron volts. The distance will be expressed in Bohr. So one Bohr is defined as A sub 0, which is 0.5292 angstroms, which is equal to minus h bar squared 4 pi, the permittivity constant divided by the mass of the electron times E squared. Now there's no prime on the E because now we're doing MKS units. So the energy in the ground state is equal to minus 1/2 Hartree, or A sub 0 is roughly equal to A. So we get R, which is a function of the quantum numbers N and L of R. It depends only on R. So for R, we get 1s, that's equal to 2 times Z over A to the 3/2 times E to the minus ZR over A. So A, remember, is equal to h bar squared over the reduced mass mu times E prime squared. And then R for 2s is 1 over the square root of 2 times Z over A to the 3/2 power times 1 minus ZR over 2A times E to the minus ZR over 2A. And then var R for 2p orbital, that's equal to 1 over the square root of 24 times Z over A to the 5/2 power times R times E to the minus ZR over 2A. Okay, and then A to the 3/2 times R of R. So that's what's graphing on this side. So here's a 0, 2, 4. This must be, what the heck is our, R over A. So radius divided by A. So as you can see, here's your 1s orbital. It goes down. Let's see, which one's 1s? Okay, one of these is 1s. Must be that top one. So anyway, here, 1s, 2s, and 2p. Notice R0 is not equal to 0. We're going to be talking about that in just a bit. So here's the tricky part. The graph is misleading because an atom is a sphere, not a circle. Now from that graph you might think the electron can actually be found in the nucleus, but it can't. So for S states, remember L is equal to 0. So this Y of L and M is going to be equal to phi and theta. No, theta of theta and phi sub M of phi. That's constant. Those are constants, both. So remember, like I said, this Y of L and M, that's spherical harmonics. So we get Y00 is just 1 over 4 pi, square root of 4 pi. So we have the psi of 1s orbital is equal to 1 over square root of 4 pi times 2 times Z over A to the 3/2 times E to the minus Z over ZR over A. That's equal to 1 over the square root of pi. Oh yeah, that was squared. Did I write that wrong? Times Z over A to the 3/2 times E to the minus ZR over A. And again, A is equal to minus H, or equal to H bar squared over mu times E prime squared. See handout figures 73 and 74. Now, in this case, there's no sine or cosine because the spherical orbital, it's spherically symmetric. And then by the S shells, of course, you might guess they get bigger with higher N. So like a 1s orbital is the smallest orbital, and then a 2s orbital is the bigger orbital, and then the 3s orbital is the bigger orbital. Now let's talk about molecular orbitals. So here's a, let's see, I want 2 pz and pi 2 px and pi 2 p4, py, x, y, z. So all wave functions have the nodes at the nucleus and infinity, but we're going to ignore these when we're counting nodes. That doesn't count. So the number of nodes in practice is n minus 1. See table 19.1. So p orbitals, they have direction, but s orbitals don't. So P wave functions have the angle components, theta and phi, in their formulas. Now squaring r of r doesn't give probability. It's spherical, so we get 4 pi r squared r of r. But then we have to integrate that to find probability. So here's wave functions of degenerate energy levels. Okay, let's say we have energy level 1, which psi 1, psi 2. If the Hamiltonian of psi 1 is equal to energy level 1 times psi 1, and Hamiltonian of psi 2 is equal to energy level 1 times psi 2, then the Hamiltonian C1 psi 1 plus C2 psi 2 is equal to E1, excuse me, C2 psi 2 plus C2 psi 2. That's what we call a linear combination. So any linear combination will work as long as the wave functions are at the same energy level and is normalized. In other words, C1 squared plus C2 squared is equal to 1. But it's not true that if the wave functions have different energy levels. So if we have like E2 psi 6 and E1 psi 5, then the Hamiltonian of psi 5 equals to E5 psi 5, and the Hamiltonian of psi 6 is equal to energy 6 times psi 6. But we can't say that the Hamiltonian of C1 psi 5 plus C2 psi 6 is not equal to the energy of C1 psi 5 plus C2 psi 6. Now let's talk about real wave functions. So let's say we have n equals 2, L equals 1, and m equals positive 1. So here we have a 2p plus 1, that's our m value. It's going to be equal to b, that's just some constant, times e to the minus zr over 2a, times r sine theta, e to the I phi. This is complex, obviously. So b is defined as 1 over 8 over the square root of pi. Remember, equal sign with 3 lines is defined as, are always equal to. Times z over a to the 5 halves. Okay, and then r sine phi, e to the I phi, those are spherical harmonics. So we get 2p minus 1, that's equal to b e to the minus zr over 2a times r sine phi e to the I phi. And that obviously is complex. And then r sine phi is equal to x over cosine phi. And c is defined as 1 over minus 1 over the square root of pi times z over a to the 5 halves. So TP0 is equal to c times e to the minus zr over 2a times r cosine phi is equal to 2pz. This is a real function. So e to the I phi is equal to cosine phi, whatever, plus I sine phi. That's called Euler's relationship. So we have e to the I phi equals cosine phi minus I cosine phi. So we have 2px, that's 1 over the square root of 2, times 2p minus 1 minus 2p plus 1. That's a real function. So this 1 over the square root of 2, that's the normalization constant. Now 2p, that's the name of the function. That's not a constant. So we have 1 over the square root of 2 squared plus 1 over the square root of 2 squared is equal to 1 half plus 1 half plus 1. So that's normalized, because remember, if it's normalized, the function should add up to 1. And then 2py, that's 1 over I square root of 2 times 2p minus 1 minus 2p plus 1. See table 19.1. Now we want to show, WTS stands for want to show, 2px is equal to 1 over the square root of 2 times 2p minus 1 plus 2p plus 1. Okay, then see the handout from May 22nd. So we have psi of 1s is equal to 1 over square root of pi times z over a to the 3 halves times e to the minus zr over a. We're going to plot the square of that. So here we have psi of 1 over s squared versus r. As you see, it's curving down. So you see psi over 1s squared is proportional to a radius squared. So from this, again, it seems like the electron's most probable place is going to be in the nucleus. But again, that's wrong. And it's misleading because this is only the radial portion of the function. So instead, we have to multiply by 4 pi r squared so that we're doing a sphere instead of a circle. So here's an atom. We're at some radius here, and then this is supposed to be infinitesimally different, like really close together. So it's R plus dr. It's exaggerated so you can see it's a circle within a circle. So the outer volume, well, the inner volume, of course, would be just 4 thirds pi r cubed. So the outer volume would be 4 thirds pi r plus dr cubed. Now simplifying that, we get the difference between the outer volume and the inner volume. It's just 4 pi r squared dr. Now we're going to multiply psi 1s squared by 4 pi r squared dr. So we get, here's 4 pi r squared times the psi 1s squared against r. This is what it looks like now. This gives us the most probable radius is 0.529 angstroms for hydrogen, obviously, and for only a 1s orbital. See note figure 251. So the curve starts at 0, 0, so there's no probability of finding the origin in the nucleus. And likewise, we're going to find the peak radius, just take the derivative and set it equal to 0. Hopefully you learned that in differential calculus, like the first few weeks. So the derivative with respect to radius of 4 pi r squared times this psi of 1s squared is equal to 0. So then we get r is equal to a over z. Z is equal to 1 for hydrogen atom. R is equal to a is equal to 0.529 angstroms for hydrogen. Now remember, the average value is also the expectation value. We already mentioned that. And the average value for the radius is our distance. So we have average m is the integral from all space of psi star times m hat psi d tau. Now in this case, r is m hat. So we get average value for r, or the expectation value for r, is the integral from 0 to 2 pi, that's for the phi angle, and then the integral from 0 to pi, that's for the theta angle, and then the integral from 0 to infinity for radius, and we get psi star of r hat psi r squared dr sine theta d phi. Now d tau in spherical coordinates is r squared dr sine theta d phi. And in this case, r hat is just r. So spherical harmonics drop out since they're already normalized. So we just get the average or expected value for r hat, or r, is the integral from 0 to infinity of psi star r psi r squared dr. So all three integrals are normalized. So for 1s orbital, we get this theta of 0, 0 theta is equal to the square root of 2, and phi is 1 over the square root of 2 pi. So we get the integral from 0 to pi of theta squared of theta sine theta d theta, that's equal to 1, so that's normalized. We also get the integral from 0 to 2 pi of phi squared d phi, that's also equal to 1. We get the integral from 0 to 2 pi of 1 over 2 pi d phi is equal to 1 over 2 pi phi evaluated from 0 to 2 pi. So we get 1 over 2 pi times 2 pi minus 0, that's equal to 1. And then likewise, we get the integral from 0 to pi of the square, the square root of 2 over 2, times sine theta d theta, that's equal to the square root of 2 over 2 squared, times the integral of 0 to pi sine theta d theta. That's equal to 2 over 4 times minus cosine theta, evaluated from 0 to pi, and we get 1/2 times the whole quantity minus cosine pi plus cosine 0, and that's equal to 1/2 times 1 plus 1, that's equal to 1. So all the phi and the theta and phi are normalized. So y of Lm phi theta, they're spherical harmonics. Those are normalized. Now let's do a complete description of the orbital. So an orbital is a one electron spatial wave function. All orbitals have the form of psi based on NLM quantum numbers, and they can be written as a function of r, which is a function of the NL quantum numbers, and the angle y, which is LM quantum numbers. The shape of an orbital is defined as a surface of constant probability density that encompasses some large fraction or percent, say 95% of the probability of finding the electron. So for example, we have psi of 2pz that's equal to 1/2 2 pi to the minus 1/2 power times z over a to the 5/2 times r times e to the minus zr over 2a cosine theta. So here's a graph z versus x. So here's function. Here we have two identical circles that are not touching. This is for a p orbital. So we have cosine is plus, oh no, cosine is, if cosine is positive, that's for the angle 0 to theta to 90 degrees. And then for cosine is negative for the angles 90 to 180 degrees. So they're shaped like circles because we're talking about cosine here. Now if you take that function squared, then we have still versus z versus x, but we're on the x, y nodal plane here. This is the xy nodal plane. So y is coming out of the paper, obviously. So as you can see, it's the more familiar dumbbell shaped. So see handout figure 75 to 79. And that's it for section 3.